We say that an object is in a state of free fall, it is free falling, if the following four things are true. Number one, it is not in contact with any other object or surface. It's not touching anything else. It's up in the air, not in contact with anything. Number two, it's not being acted upon by the air itself. Here are four examples of objects that are interacting with the air. So all four of these are not in free fall. Here is a meteor moving this way through the atmosphere. It is experiencing a drag force on it as it moves, an air drag. Here's a balloon experiencing a buoyant lift. Here is an airplane with a lift force due to the motion of air over its airfoils. Here is a helicopter with thrust due to the motion of the propeller, and a bird who gets a flapping thrust. It's kind of like an air drag against the wings. So all of these are interacting with the air, therefore they are not in free fall. Number three, the object must not be subject to a rocket type of thrust, like our bottle rocket here. Now, this is a separate category from all of these because a rocket can still propel itself in vacuum, in space, by expelling hot gas to drive the body of the rocket forward. None of these effects occur in a vacuum, but this will still work in a vacuum, therefore it's a separate category. This is not in free fall either if it has some kind of rocket thrust. So then number four, if none of these things are allowed to happen, the only force acting on the object is gravity. And if these are all true, then we say the object is in free fall. Now, if the object is in free fall because it satisfies all four of those conditions, and it's near the surface of the Earth. So if we're in free fall and we're near the surface, that means within a few kilometers of the surface. Experiments have shown, time and time again, that the acceleration of that object as it moves the whole time it's in free fall, its acceleration is constant, and its components are constant. The vertical component will be negative 9.8 meters per second squared if down is our negative y direction, and the horizontal component will be 0. Therefore, the magnitude of the acceleration will be 9.8 meters per second squared. That's, of course, approximately 9.8 meters per second squared. Let's look at some examples of objects that are in free fall. Okay, here are a bunch of penguins moving through space, and most of them are in free fall. The red arrows indicate their acceleration vectors. And note, for all of them that are in free fall, their accelerations are pointing straight down, their y component is negative 9.8 meters per second squared, and their x component is 0. There is no component of the acceleration in the x direction, in the horizontal direction, if you are in free fall. And that's true no matter what your velocity is, whether you're moving this way upwards, or this way down, or you've reached the top of your motion and for a moment you're just moving that way. No matter what your velocity is, your acceleration, if you're in free fall, is straight down. So the word free fall sort of implies that something is falling downwards, but by our definition, even though this one is moving upwards, it is in free fall because it's not in contact with anything, it's not being influenced by the air, it doesn't have a thrust to it, and the only thing acting is gravity. Therefore, even though it's moving upwards, it's in free fall. I'm not sure what's up with this guy right here. His velocity is 0 at the moment. Maybe he was going straight up and we've caught him frozen in time just at the very top of his motion before he's about to fall back downwards. Over here, this penguin is, this one is in contact with this surface, therefore this one is not in free fall. And it's not in free fall the whole time it's touching the surface, but the instant that it loses contact, the instant its belly lifts off the surface right there, then it will be in free fall. And we've caught that penguin just at that instant. He's just left the surface, he's not in contact anymore, therefore he's in free fall, and his acceleration is down with a magnitude of 9.8 meters per second squared. This penguin bounced off the ground. for a moment here, while he was in contact with the ground, he was not in free fall. But now he's up in the air, he's in free fall again. So it's free fall before and after, but not during the time he was touching the ground. This one is also in contact with the ground at the moment, therefore he's not in free fall at this moment. Let's look at the equations of motion that we'll need to describe the motion of an object in free fall. So here were our equations for an object moving with constant acceleration. Now we determined that from experiment, in free fall, the x component of the acceleration is 0. Therefore, this whole side goes to 0, this term here goes to 0, this term here goes to 0. What's left is that the change in your x component of the velocity is 0. Therefore, it's not changing. Therefore, the x component of your velocity is constant as long as you're in free fall. Since this term dropped out, this is all that remains here. So we see that for your horizontal motion, it's a simple distance equals rate times time relationship. And that's all we really are left with here on the horizontal side. This equation here just reduces to this one. So really just two relationships left here on the horizontal side. And then on the vertical side, all of these AYs, the y component of the acceleration, you can replace all of those with negative 9.8 meters per second squared if you are in free fall. So it simplifies to this. Here are our equations of motion for projectiles. A projectile is defined to be an object that's in free fall. And I've just summarized what we just went over. These are your two horizontal equations, and these are the remaining vertical equations with negative 9.8 meters per second squared put in for the y component of your acceleration. We're assuming that down is the negative y direction. That's why there's a negative sign on all these y components of the acceleration. And one last key point, an object must be in free fall the entire time between events 1 and 2 for these equations to apply. So for instance, this penguin right here, we could not apply those equations to the moment when he was here and the moment when he was here. Although he's in free fall here and here, in between these two events, he hit the ground, so he was not in free fall during this time. Therefore, we could not apply the equations of motion to this penguin from events here to here, because he wasn't in free fall the entire time.